basically, we're going to talk a little bit more about the cache structure and how to manage the cache. And this is just for you to recall what we're talking about. We have a tag store and a data store. And recall that we talked about set associativity last time. And this is essentially how do you organize the cache. Where can a block address in memory map to? If it maps to only one possible location in the cache, one possible physical location in the cache, that means it's a direct map cache. If it maps to two possible locations, like in this cache, it's a two-way set associative cache. And now you have the freedom to place the block into either location. And if you have an access pattern that repeats, like address A, B, A, B, A, B, A, B, A, B, you can accommodate both of those blocks inside the tag store as well as the data store. So that's the idea of set associativity. Of course, this complicates things, but you pay a cost for everything. There's a plus side for everything, which is accommodating conflict misses better in this case. And the downside is you pay a latency penalty and complexity penalty and hardware area penalty. Okay, so let's talk about what's in a tag store entry. Clearly, I showed you two things over here, a valid bit and a tag. And these are the minimum that you need. But you need something else we've discussed last time. What is your replacement policy, right? For example, if you have here address A and B, and they're occupying way 0 and way 1 over here, and if you need to fetch C into the cache, which one do you evict? So you need to consult your replacement policy to be able to do that, and that may require some bits, unless it's random. So if you're doing random selection, you need to somehow generate a random number and decide which one to evict, right? And you may randomly pull a bit from some wire in the processor to be able to do that, but we're not going to go into that. As we've discussed, least recently used policy is one policy. And if you actually have a two-way set associative cache like this, you need only one bit over here to the side to say which one is the least recently used in a given set. If it's 0, it would be way 0. If it's 1, it would be way 1. And we've discussed that this gets more complicated as you increase the associativity, right? I'll make a point before we move on a little bit, but I showed the associativity of 2 over here. Could you have associativity of 3? That's not a multiple of 4, right? And I see nodding heads. And the answer is actually yes. You can have an associativity of 3, right? Because you're not using the bits to index. The bits to index, it needs to be a power of 2. Otherwise, you'll lose some locations perhaps, right? But you could have an associativity of 3 over here. Let's say 3 blocks of 4 entries each, or 4 sets each. We can have way 0, way 1, and way 2. And for the data store, we can have way 0, way 1, and way 2. All we need to do is to ensure that we do the tag match, and one of the 3 may match, and we do the muxing correctly, selection correctly. So associativity can be any number, actually. It doesn't need to be a power of 2. In fact, one of the IBM processors, I believe Power 4, had 3-way associative cache, or 12-way associative cache. It was not 16 or 8. It was 12 ways. And the reason is, for associativity, you're doing content addressable search, right? You're really searching the tag that you have in the address, and you're looking up that tag in way 0, way 1, and way 2. You could have an arbitrary number of ways. You're not limited to a power of 2. Makes sense, hopefully. Okay. So what's in a tag store entry? I've already discussed this: valid bit, tag bits, and replacement policy bits. So there will be some exercise in your homework where you can actually calculate the size of the tag store. Or given the size of a tag store, you can, with enough information, you can calculate how big your cache block size is, for example. It's fun. You can do all of these things. There's also something else which we didn't discuss, and this relates to how do you handle writes into the cache. And it's called a dirty or modified bit. So I'll introduce this right now. So dirty bit indicates that the block that you have in the cache is dirty, meaning that you have written to it, but you haven't updated memory. So the contents of the cache are dirty or modified with respect to the contents of memory or the next level. That's the idea. And it happens if you have this design choice where your cache is write back. So what does that mean? So writes actually pose some problems in caches, so I'm going to handle writes a little bit. The first key question is, when do you write the modified data in a cache to the next level? You have a store that commits, and you need to write the data into the cache. And now you have a choice. Do you just write it to the cache, or do you write it to this first level cache, or do you write it to all of the levels underneath, and even maybe main memory? So that's what write-through is. If you actually write it to all of the levels, you're making a choice. You're saying, whenever the write happens, I'm going to update all of the caches in the multi-level hierarchy, including the main memory. Of course, you could have a subset of the caches obeying the write-through policy, right? It doesn't have to be all of the caches. Write back, on the other hand, means I'm going to update only this cache, and I'm not going to update anything else at this point. Only when this block needs to be kicked out from the cache, evicted from the cache, then I'm going to take that block and write it back to the next level. That's why it's called write back. You're writing it back at the time when the block is evicted. This is one of the fundamental design choices in a cache, and it has both of them have advantages and disadvantages, which we will talk about. In write back, for example, what might happen is, let's say you have a 64-byte block, and you're doing a lot of writes, store to an array. And you're doing stores that are 4 bytes each. Basically, you would be writing 4 bytes to this part of the block. You would be writing 4 bytes to the next part, 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 ... Right? Which means that all of those writes now need to go through the cache, clearly L1 cache. But if you actually had a write-back policy, no other cache needs to be informed of this, right? Which means that you would save bandwidth between the different caches. So think about L1 cache and main memory. You have a store instruction. Store is doing a 4-byte write. You would keep it in the cache, L1 cache, if you have a write-back policy. If you don't have a write-back policy, if you have a write-through policy, that 4 bytes needs to go to the L1 cache as well as main memory. And remember that the bandwidth to the main memory is very low, which means that we would be wasting that bandwidth. So if you actually have multiple writes or multiple stores that are writing to the same block, you could combine those writes if you have a write-back cache. And this is very powerful. You may see this. Think about you're copying one array to another. You have very good spatial locality, right? You would keep writing on a 4-byte basis to the entire array. It makes no sense to expose all of those writes to the main memory because that would waste bandwidth, right? Just keep it in the L1 cache. That's the benefit of write-back cache. It saves bandwidth between cache levels or between cache to memory. It also saves energy. Clearly, doing many, many writes to all of the caches is not energy efficient. But the downside is, again, you have area cost, right? You need a bit to tell you that the block is dirty or modified. Because if you, essentially, it's a consistency problem. The block that you've written to, at some point needs to be written back to memory, and you need to know that you need to do that at some point. So whenever you do the write, you set the dirty bit, and whenever that blocks get evicted, there is a cache controller that checks that dirty bit, and if the dirty bit is set, it writes that block back to the next level in the hierarchy. So hopefully this is very simple. Okay, so why do we do write through then? This makes sense, right? Why don't we always do write back? Because it saves a lot of bandwidth. Well, write through is simpler. That's one thing. You don't need dirty bits. That may not always be a good reason. Simpler may be low performance also. But there are other reasons also we will get into at the end of this particular lecture. And this is the idea of consistency or coherence. Essentially, if you actually write through to all caches levels are up to date. Now, suppose that there's some other processor that needs the same block. Now we're getting into a little bit more advanced concepts. Some other processor that needs the same block. It has access to only the main memory. It doesn't have access to this processor's cache. If you do write through, this other processor can get the data without any problem, right? Correct version of the data. Whereas if you do write back, this processor that updates its L1 cache will have some data in the cache. Memory will have some other old value. It won't have the updated value. And what does this processor get? There's a consistency problem because this processor has written to that block, L1 cache is updated, memory is not updated, some other processor wants to read that block. Which value should it get? Well, that's the consistency problem. We will get to that at the end, or coherence problem. And of course, write-through, a big disadvantage is it's more bandwidth intensive because there is no combining of the writes. So today, a lot of the caches are actually write-back, but in some cases, write-through also occurs. But bandwidth is very, very important today in today's systems. As a result, many caches that you see in real systems are write-back. But that doesn't mean that write-through doesn't exist because of these reasons that we discussed. Okay, there are a bunch of other questions related to writes. Let's tackle another one. Let's say you have a store instruction. You want to store to a memory location, let's say 4 bytes. Do you bring the entire cache block into the cache and put it into the cache? In that case, 64 bytes. That's the key question. If your answer to this question is yes, then you're following the allocate on write miss policy. Basically, you try to write into the cache, it misses, and then you bring the entire block into the cache. If your answer is no, then you're not allocating on a write miss. So we've always assumed so far you would allocate on an access, but we didn't distinguish between writes and reads, right? So what is the benefit of allocate on write miss? Again, if you actually allocate on write miss, you can combine writes instead of writing each of them individual to the next level, right? So if you don't allocate on write miss, what happens is you don't write the 4 byte into the cache, you write it directly to main memory. Let's assume that you have L1 and main memory. If you don't allocate the cache block on a write miss, you would write the 4 bytes into main memory. And you would keep doing that if you keep writing 4 byte, 4 byte, 4 byte, 4 byte, 4 byte, 4 bytes, right? So essentially, you're bypassing the cache in this case, right? So, but if you're allocating it, you would, whenever you do the first write, you bring the cache block into the cache first, and then you do the write. And then if you're going to write to that block again, it hits in the cache, and you keep doing the write to that block. So perfect, caching works nicely. But because you've allocated on a write miss. So that's the benefit over here. And it's also simpler because write misses can be treated the same way as read misses, right? For read misses, we never said, oh, do you actually bring the entire block into the cache? You have that choice also in modern processors, but we basically said, whenever you access some data, you bring it into the cache. In this case, if you actually do the same thing for reads and writes, you don't need to have a separate logic to decide that. So it's a bit simpler. Now, the downside of allocating on a write miss is it requires the transfer of the whole cache block. Now, think of some write that you're doing to memory that doesn't have very good locality. You just want to update this bit in this part of the array, and you're not going to modify anything else. And you're not going to touch that data for a really long time. Does it really make sense to bring the entire block into the cache? Why not just write that bit into the memory? So that's the idea over here. Basically, that's the downside. So no allocate. If you don't allocate on a write miss, it conserves cache space if the locality of writes is low. So basically, if you don't allocate, you don't disturb the cache. And if you're doing only one random write to one location in memory, there's no reason to bring the data, the cache block into the L1 cache. You save bandwidth, but you also save cache space. Make sense? Okay, you can think about it a little bit. But this is one example of a policy, actually. You may have the question, okay, why are you talking to me about this just for writes? I have the same option on reads also, right? And that is true, actually. You have the same option on reads. You can decide not to bring the cache block into the cache. If you, for example, say, oh, I'm doing a random read, and I don't have good spatial locality. But this requires some prediction mechanism now, right? You need to be able to predict whether you will have good locality or not. And existing cache policies are actually much, much more complicated than what we've discussed. They do things like that. But we don't have time to cover them. Okay, let's have a little bit more fun with writes. Basically, another question, which actually we kind of covered, but I'm going to introduce a new technique that handles this better. What if the processor writes to an entire block over a small amount of time? This is called a streaming write. Let's say you have a 64-byte block, and you're writing to that block 4 bytes at a time. Because if you think about the store instruction, store word instruction in MIPS, for example, it writes 4 bytes. It doesn't write 64 bytes. There is no instruction that writes an entire 64 bytes. Instructions operate on the granularity of the register sizes, right? Register widths. So you write only 4 bytes. But let's assume that you're writing to all 16 of the 4 bytes in a 64-byte cache block. That's called a streaming write. Essentially, you're streaming through memory. Again, copying one array to another is an example. If somebody who thinks may ask the question, can we do better for these cases? Is there any need to bring the block into the cache from the memory in the first place? If you're going to write to the entire block and modify it, and if you have a write-back cache, well, it doesn't matter write-back or write-through, actually. You don't really need to read the entire block into the cache at all, right? Because you're going to reconstruct that cache block inside the processor. You're going to do 16 writes, and if you do all of them into the cache, now that's your 64-byte block. There's no reason to read it from memory. Basically, the key question is, why do we not simply write to only a portion of the block whenever you have a store? And this is called a subblock. For example, 4 bytes out of 64 bytes. So you need to change the cache structure to be able to do this, because you have a problem, right? The cache that we've discussed, the 64 bytes, was a block. And you had valid and dirty bits associated with the entire 64 bytes, not with each individual 4 bytes. You cannot really write to just these 4 bytes and assume that everything is okay. You cannot say, oh, the block is valid, because what happens to the remaining 60 bytes, right? You didn't bring it from memory. So you need a separate cache structure to be able to do this. And the idea of subblocked or sectored caches is, it was actually introduced in that IBM paper that I mentioned earlier, that exploited spatial locality, the LibTay paper. And the idea is to divide a block into subblocks or sectors. And it looks like this, basically. This is the block, and this is the tag for the block, very similar to what we've done before. But you associate different valid and dirty bits with the subblocks. This way, you can allocate only a subblock on a request, or a subset of subblocks. You have more flexibility. Let's assume that you're doing a 4-byte write to this subblock. The processor doesn't need to bring anything into the cache. What it does is, it sets the valid bit here, it sets the dirty bit here because you're doing a write, and it writes to the subblock whatever data that the store instruction produced, 4 bytes, and of course it needs to set the tag, right, accordingly. Now you have an entire block allocated to the block that has this tag, but 15 of the subblocks are invalid, and 1 of them is valid and dirty. Makes sense, right? This way, you don't need to bring the entire block just to do a 4-byte write. Now, the next write goes to the next subblock, you do the same thing. The next write goes to the next subblock, you do the same thing. So you can actually combine the writes in the block without ever bringing the data, bringing the older version of the block into the cache. So that's the idea over here. It's very powerful, because you don't need to transfer the entire cache block into the cache. A write simply validates and updates a subblock, and of course that's the dirty bit. And now you have more freedom in transferring the subblocks into the cache, right? A cache block doesn't need to be in the cache fully, right? And there's a question, of course, right? Can you actually use this for reads? And again, the answer is yes. If you have a good predictor, the predictor can say, oh, I'm going to need blocks 0, 5, 7, 8 in the next, I don't know, a few nanoseconds, for example, or a few milliseconds. So I'm going to only fetch those. If you're smart enough, this way you save memory bandwidth, because you're not bringing the entire 64 bytes into the cache, you're bringing the subblocks that you think you need. So it's a very powerful idea. But the downside, of course, is always more complexity in design, right? If you look at this, you didn't increase the size of the tag, but you added valid and dirty bits per subblock. So if you have 16 subblocks over here, you have 32 valid bits and 32 total bits, as opposed to having only 2 bits per block, right? So it's expensive. But the benefits may outweigh the expense. And of course, there's another downside. It may not exploit spatial locality fully, right? For example, if you said, okay, I'm going to allocate the subblock when I do a write, but let's say your next access is a read to this subblock, then you will miss in the cache, and you need to bring that subblock, or you need to make a choice of which subblocks to bring at that time, right? So you may not be able to exploit spatial locality fully because you're not bringing the entire cache block into the cache. So it's important to optimize these decisions, like when do you bring a subblock, which subblocks to bring, and when to evict. Okay. So writes are done. There's more, but we don't have time for more. So let's take a look at some other design decisions in caches. Separate instruction versus data. Should they be separate or should they be unified? This is a question that people asked many times. Unified means instructions and data are placed in the same place. What does this mean? I mean, if you know the von Neumann architecture, there's really no distinction between instructions and data. Everything's in memory. But the distinction is when do you actually touch that location? If you're in the fetch cycle of the instruction phase, fetch instruction phase of the instruction cycle, the program counter, you take the program counter, add it to memory, and interpret that data as an instruction. Right? Now, do you put the instructions that are fetched in the instruction fetch stage into the same cache as the data that are fetched by the loads in the data fetch stage? If you put them together, they're unified. Now, unified may be good because this enables dynamic sharing of cache space. Meaning, if you have separate instruction and data caches, let's assume that you have a 64 kilobyte instruction and 64 kilobyte data cache. And let's assume that the program is such that it doesn't work on a lot of instructions. The instruction working set size, the amount of instruction footprint that you touch in the entire program is 1 kilobyte. So you have 1 kilobyte instructions, and you have a 64 kilobyte instruction cache that you've designed. This is an over-design, right? This is over-provisioned. And if you have a let's assume for the same program, you have the 64 kilobyte data cache, but the program needs to access 128 kilobytes of data, or let's say 127, just to make the example nice. You have only a 64 kilobyte data cache that you've designed, but you're touching 127 kilobytes. That's terrible. Your cache is thrashing in this case. You don't have enough capacity in the cache. But if you look at both of the caches in aggregate, you actually have 128 kilobytes. If you design the two caches to be unified, you would have a single 128 kilobyte cache, and you could keep the 1 kilobyte instructions and 127 kilobyte data in the same cache, and you won't see any misses. That's the upside of unified. The exact opposite can happen also, right? You could have 127 kilobytes of an instruction working set, which doesn't fit into the 64 kilobyte instruction cache you designed, and only 1 kilobyte of the data working set. That's usually not the case. Usually data is much larger than instructions, especially today. But basically, if you have a unified cache, you can dynamically share the space as opposed to statically partition the cache. And static partitioning is always bad in cases where you have this kind of imbalance in the working set. But the downside is, if you have a unified cache, instructions and data can thrash each other. There's no guaranteed space for either, right? They can kick each other out of the cache, right? So you could actually construct a similar example where both of them are 65. I don't know. You could construct a similar example, basically. At least if you have an instruction cache dedicated to instructions, you will have some good hit rate in the instructions, and you could be fetching the instructions, right? And data cache with 64 kilobyte dedicated for data, you will have some good hit rate. But if you combine them now, what might happen is the data can kick out the instructions can kick out the data, and you would be stalling in different parts of the pipeline for many reasons. Okay, actually, this last reason is the main reason why most processors, actually all processors that I know of, implement separate instruction and data caches. And the main reason is instructions and data are accessed in different places in the pipeline. And you know that very well. If you want to, the fetch stage, you have a program counter that needs to access the instructions. An instruction cache is placed over there. And data is accessed when you actually, after you generate the address of a load or store, and that needs to be accessed in some other part of the pipeline. And remember that caches are always integrated, L1 caches are very integrated into the pipeline. That's why you need to supply the instructions right away into the fetch stage. And the pipeline works nicely that way. And then when you get to the data access, memory access stage, you have another cache over there, that's the data cache. Okay, so basically if you had a unified cache, where do you put the cache? Is it close to the fetch stage? Is it close to the memory access stage? You could put it in the middle, but now you need to wire. You need to do the wiring such that both stages are connected. Now your wiring becomes also simpler if you actually separate the caches and put them in different stages. Okay, so for this reason, for this last reason above mainly, first level caches are almost always split or separate, but higher level caches are almost always unified between instructions and data. So if you look at the L2 cache, L3 cache, there's no distinction between L2 I cache or L2 D cache. They're all unified for mainly this reason, actually. Dynamic sharing of cache space. So this way you kind of get the best of both worlds. You satisfy, you don't get the downsides at the L1 level, and you get the upside at the L2 and L3 level. And these may be less important at the L2 and L3 level. So now you can see that the cache design is different at different levels because you have different constraints at different levels. Okay, so that brings me to the next point, which I already covered last time, actually. So if you have multi-level caches in a pipeline design, you have first-level caches. Instruction and data are usually separate. And the decisions are very much affected by the frequency of the processor, the cycle time. As a result, first-level caches are usually smaller, lower associativity, because latency is critical for them. And as a result, again, tag store and data store are accessed in parallel. We discussed this also, so that you can get the data quickly if you hit in the cache. If you miss in the cache, you waste some power. But these caches are small, so maybe they don't waste as much power. So second level and further caches, today we have 3, 4 levels. Decisions need to balance the hit rate and access latency at that level, because access latency is not as critical at those levels. Usually they're large and highly associative, especially if you go to third level, for example, or fourth level. Latency is not as important because you could potentially, hopefully you have a good hit rate over here. The access to these levels don't happen much. And also for saving power, tag store and data store are usually accessed serially. You access the tag store first, you figure out whether it's a cache hit or miss. If it's a hit, only if it's a hit, you access the data store. Because these are very large caches, very large data stores. You don't want to access those large things without knowing that you have a hit or miss. You can pay the additional latency penalty to figure out whether it's a hit or miss first, and then access the data store and save a lot of energy. So that's a clear trade-off between latency and energy. I pay the additional latency so that I can save energy. Right? And if you look at modern processors, they, maybe not in second level all the time, but third level, fourth level, they almost always do make this choice, serial access. There's also another thing. These are tag and data stores accessed serially. In a multi-level cache, you have another choice. Do you access the level 1 first, and if you miss, you go to level 2. And if you miss there, you go to level 3. This is a serial access. Do you serialize the access to different levels? Or do you do them in parallel? That's a choice also, actually. Basically, serial means second level cache is accessed only if first level misses, which means that second level does not see the same access as the first. And first level acts as a filter in this case. So it filters out some temporal and spatial locality. So what's the benefit of serial access? Clearly, if you access all of the levels in parallel, that's a lot of power consumption. And it's only beneficial if you miss in the first level and if you hit in the second level, right? Assuming 2-level cache hierarchy. But that could be important, right? So, but the downside, so what is the upside of, parallel access is essentially you get the benefit if you miss in the first level and if you hit in the second level. That's the upside. The downside is you save a lot of energy. you expend a lot of energy, right? To actually access both levels at the same time. Maybe not a good idea. So most of the time today, cache levels are accessed serially. You access the first level first, and then if you miss, you access the second level, and if you miss, you access the third level. As a result, first level cache, or different levels act as filters to the later levels. They filter out some temporal and spatial locality. And this is exactly the reason you need to manage them differently as well, another reason. Because the access pattern that you see in the first level is the access pattern that the processor has, but the access pattern that you see in the second level, now it's filtered, right? It's something else. Everything that doesn't hit in the first level is accessing the second level. Okay, therefore you have different management policies. Any questions? Okay, let's talk a little bit more about cache performance. We talked about it a little bit, but let's talk about it more. Even with these design choices, there's a lot more design choices. It's a complex trade-off space. So basically, there are a bunch of cache parameters that affect the hit and miss rate: cache size, block size, and associativity, and replacement policy, and insertion and placement policy. So these affect the miss and hit rate, but they also affect the latency of the cache also. But we're going to take a look at miss and hit rate mostly in the graphs. But we will also, you need to consider hit latency and miss latency as well, right, as we've discussed before. Let's take a look at cache size. So whenever we refer to the size of a cache, we normally talk about the data store size. So when people say, oh, we have a 32 megabyte cache in this new processor, that refers to the data store size. They don't talk about the tag store. So if you really want to know the full cache size, you need to add the tag store size to that. So having a bigger cache usually exploits temporal locality better because it can capture more things into the cache. So hopefully you can keep things more around in the cache. So temporal locality over a longer period of time is captured. But that's not always true. It depends on the program, of course. So you usually get a curve that looks like this. So this is the cache size, and this is the hit rate that you get, all else being equal, associativity, for example. You keep increasing your hit rate, but at some point, your hit rate doesn't increase because your working set, for example, fits in the cache at that point, right? And your hit rate may not always go to 100% because whenever you first start accessing the cache, there's nothing in the cache, right? There are some compulsory misses, which we will also talk about. Now, if you have too large of a cache, that's also not good, depending on your trade-offs. This adversely affects hit and miss latency. It takes longer to access that cache, and we know this very well. Smaller is faster, which means that bigger is slower, and access time may degrade the critical path, especially if you're doing the L1 design. This is much more of a problem in the L1 caches. But if you have too small of a cache, you have another problem. It doesn't exploit temporal locality well, and useful data is replaced often. So you need to decide the size of your cache clearly, and we discuss this. So what is working set? We've discussed this before, but this is essentially the whole set of data the executing application references within a given time interval. This is not very, if your time interval is specified, you can calculate how much data the application actually touches during that time interval, right? Okay, that's true for instructions also. Okay, let's take a look at block size. This is a little bit more interesting, maybe. Block size is essentially the data that's associated with an address tag. And usually you have a curve that looks like this, assuming the cache size is constant. So given a cache size, let's say 1 megabyte, do you want to have 8-byte blocks or 64-byte blocks or 1 megabyte block? So if you have 1 megabyte block, you have only 1 block in the cache. If you have 64-byte blocks, you have somewhere in between. If you have 1-byte blocks, you have 1,000,000 blocks, right? That's the trade-off. So if you have 2 small blocks, well, okay, yeah, we've discussed this already. If you have 2 small blocks, it doesn't exploit spatial locality well, clearly. And 2 small blocks have another downside, which is they have larger tag overheads. Remember, if you reduce the block size, you're increasing the tag store size because you need to identify that block. Your tag is large. 2 large blocks on the other end, you have too few total number of blocks. You can have 1 block, right, in the 1 megabyte cache if your block size is 1 megabytes. As a result, you exploit that spatial locality really, really well in this block if it exists, but temporal locality, if you're touching 2 different parts of memory and they're separated between each other with 1 megabyte address space, too bad, right? You're storing only 1 block. As a result, you have a curve that looks like this, basically. As your block size increases, your hit rate plateaus at some point. There's an optimal block size. Of course, this depends on the application. And if you keep increasing the block size, keeping the total data store size constant, then you lose hit rate because you're not caching enough blocks in your cache. Okay, and 2 large blocks also waste cache space and bandwidth and energy if spatial locality is not high. Basically, large blocks are good for spatial locality exploitation. But if you don't have that, you're really wasting all of that cache space and energy and bandwidth to bring the data into the cache. Okay, so large blocks, let's talk about large blocks a little bit. There are 2 optimizations that are done when you have large blocks or relatively large blocks. We've already discussed one of them. We're going to get back to it. But one of the issues is large cache blocks can take a long time to fill into the cache. Let's say you have a 64-byte block. and you need only 4 bytes for this load instruction. You missed into the cache, and you need to bring the entire 64 bytes. But how do you bring that entire 64 bytes? The load is requiring 4 bytes that's somewhere in the middle. Let's say byte 13. I just picked 13, since it's the lucky number, right? If you bring, or let me be more extreme. Let's take block 50. Let's take 4 bytes subblock. That's subblock 15 over here. If you bring the entire 64 bytes serially, first the first 4 bytes, next the next 4 byte, next the next 4 byte, the byte that you need, the 4 bytes that you need, will come at the very end. So it'll take a long time to supply that byte into the processor. So the idea that people have developed, and many processors implement this today, is fill cache line critical word first. Basically, you first fetch the critical word. This is called the critical word. The load instruction requires the 4th byte that's at the end of the cache block. So fetch that first and supply it to the processor, and then fill the cache line. That's the idea. Okay, I don't want to go into more detail about that, but hopefully this is clear. You have a more important word in the 64 bytes than others. Large cache blocks can also waste bus bandwidth. If you're, for example, touching only 4 bytes, if you need only 4 bytes, but you actually bring 64 bytes, clearly you're wasting a lot of bandwidth. And actually, sub-blocking can help. And we've already discussed this, right? And we discussed in the example of a write case. You don't waste bandwidth. You just bring the sub-blocks that you need. Okay, we've already seen this graph, actually. Associativity. How many blocks can be present in the same index? That's what associativity means, set. And basically, the graph looks like this. If you have larger associativity, you usually get lower miss rates, but at some point it plateaus again. You get reduced conflicts. But you also get higher hit latency and area costs, plus diminishing returns. Diminishing returns are shown here, but the effect of hit latency and area costs clearly cannot be shown by the hit rate. So if you have smaller associativity, you get lower cost and lower hit latency. And lower hit latency is especially important for L1 caches. As a result, L1 caches are usually less associative. But if you go to L4 caches, for example, it could be 128-way associative, right? So that you can get less conflict misses. Okay, we already discussed this power of 2 associativity required, and you know the answer. Let's classify these cache misses a little bit. This is useful to classify them. There are 3 types of cache misses: compulsory, capacity, and conflict. And I've already alluded to this, but compulsory means this is the first reference to a block, and it always results in a miss, because the cache is empty. That's the assumption to begin with. Subsequent references to the block should hit in the cache unless the cache block is displaced for these 2 different reasons. Right? And these 2 different reasons are classified in an interesting way. Capacity miss means that cache is too small to hold everything that's needed. Now, what does that mean? Because you need to have a concrete definition. What does it mean for the cache to be too small? Maybe you didn't have enough associativity, right? So we define a miss to be a capacity miss if it occurs in a fully associative cache with optimal replacement of the same capacity. Right. So if you're not doing the right thing, if you don't have enough associativity in the cache, it's not a capacity miss. If you're not managing your cache well, if you don't have a good replacement policy, it's not a capacity miss. It could be a conflict miss. Right. So basically, conflict miss is any miss that is neither compulsory nor capacity in the end. It's an interesting definition, right? But it makes sense, basically. Capacity is defined assuming you're utilizing the full associativity in the cache. And you're still missing on top of that. Okay, so how do you eliminate each miss type? We're not going to go into the detail of this. This is what the later computer architecture courses are about. And people have actually designed many, many policies of caching, not only in hardware design, but also in software design. How do you actually reduce these misses? Compulsory, well, caching cannot help. You need to be proactive. And caching, if you think about it, is a reactive mechanism. Whenever you need the block, you bring it into the cache. Well, how do you be more proactive? Proactive means anticipate what you're going to need and bring it into the cache before you need it. And that's called prefetching. We're not going to cover that, but all processors, all modern processors do prefetching. We talked about browsers doing prefetching, right? You go into a web page, and the browser anticipates, oh, you're going to click this link soon, so I'm going to prefetch all of those from the web into my cache. Right? That's an example of prefetching. Conflict misses, well, how do you reduce it? You can add more associativity, clearly, because conflict misses happen because you don't have enough associativity. Or you could try some other ways of getting more associativity without making the cache more associative. And people have been very clever in how to do that, but I'm not going to go over this. If you're really interested, you could search for these things or watch lectures from some future lectures. Okay, capacity misses, how do you eliminate that? Well, there are two things. One is you could increase the capacity clearly, but that's cheating, right? But if you, I mean, that's a reasonable thing, clearly. If you know that your capacity is not enough, in the next generation of the processor, you probably want to increase your cache size, which is what's been happening for decades in processor design, because the data set sizes are growing and you need bigger caches to hold them. But if you don't have that luxury, if you will, you have to deal with the capacity that you have in this processor, maybe you should utilize your cache space better, right? Maybe you have a better replacement policy, a better eviction policy, better placement policy. Keep the blocks that will be referenced. Or you could actually design the software to be more intelligent. In this case, you can divide the working set somehow such that you don't touch the entire 128 kilobytes or entire 1 megabyte. You touch only 64 kilobyte chunks at a time, assuming your cache size is 64 kilobytes. Right? Basically, you restructure how you access, how you do your accesses to memory in software. And this is heavily done in modern systems. It's called blocking or tiling, which we will also talk about in a little bit. Okay, so there are three fundamental goals in improving cache performance. You want to reduce the miss rate as much as possible. You want to reduce the miss latency or miss cost, or you want to reduce the hit latency, hit cost. And ideally, you would like to do all of them, but some of these work against each other, as we've discussed before. Reducing the miss rating, it requires you to be bigger, for example, and bigger means slower, meaning that both of your hit latency and miss latency increase. Yeah, that's what we said, basically. Reducing miss rate can reduce performance if more costly to refetch blocks are evicted. It's one other way of thinking about it. Basically, the above three together affect performance, and you need to be very careful in designing your cache. And as a result, people have developed many, many approaches. Again, in this course, we're not going to cover them, but I'm going to cover the software approaches a little bit before the break. And then we will take the break. But if you're really interested in some of these approaches, and this is not a comprehensive list, by the way, this is just a list, and existing processors employ even more advanced concepts, some of which may not be here, over here, or maybe they could be put into the better replacement or insertion policies. But let's take a look at the software approaches a little bit. So how can you get higher hit rate from your cache just by reorganizing your software a little bit? So you could restructure your data access patterns, or you could restructure your data layout, or you could do both. And I'm going to talk about a couple of techniques very quickly. I've already talked about blocking, but I'll talk about it more formally without giving an example, but you can think about it. And after that, we're going to take a break. Hopefully. Yeah, we will. So, okay, this will be fun. Basically, the first idea is restructuring the data layout or data access patterns. I'll give you one example. Remember the column major accesses? If you have a column major layout for an array, xi plus 1 comma j follows xij in memory. Xi comma j plus 1 is far away from xij. Now, if you want to exploit spatial locality, and if you have a column major array, you never write this code. This is a bad idea. This is poor code. What's happening here is basically you're accessing the array in a row major manner, right? As opposed to column major manner. What you're doing is, in the first iteration, you're accessing xi, comma 1. In the next iteration, you're accessing xi, comma 2, xi, comma 3, xi, comma 4, and we already said that these are far away from each other. Don't do that. Just do what's called loop interchange. And that's, in this simple case, loop interchange basically means that which way do you traverse this array? You first do the columns in the outer loop, rows in the inner loop. Basically, you do column major accesses such that consecutive iterations in this inner loop access consecutive locations in memory, and your cache exploits that, right? Your cache exploits spatial locality. Okay, it's called loop interchange, and there may be other optimizations that also increase hit rate. Loop fusion, array merging, ... which we're not going to get into. Again, a software optimization course can help here. And a lot of compiler optimizations actually do this. Compilers automatically try to recognize when to do this and when not to do this. Clearly, this can be automated, right? Okay, blocking, we already discussed it. If your working set doesn't fit into your cache, why don't you divide the loops operating on arrays, for example, into computation chunks such that each chunk can hold its data into the cache. Each working set, sub-working set fits into the cache. And this avoids cache conflicts between different chunks of computation. Essentially, divide the working set so that each piece fits in the cache. This makes sense. You don't touch 1 megabytes at a given time. You touch 64 bytes and then move to the next 64 bytes. So if you're doing matrix, if you're adding 2 matrices, I'll start with adding 2 matrices. You can easily do this, right? There's no reason to there's no reason to go through the entire thing, right? You basically chunk it such that you have this part of the matrix and then this part of the matrix, and then you use as much as possible this part of the matrix, keep it in the cache, and then add and then bring in the other matrix in chunks, such that you never evict this matrix this matrix portion that you're adding to the other matrix. Right. Basically, you do the right thing such that you minimize the hit rate, and you can program things this way. This is also called tiling. Again, I'm not going to go into this. There could be other courses where you can cover this. Let's take a look at one more example. This is an interesting example. Basically, let's assume that you have this struct. This is the C syntax. How many of you know C here? Okay, not terrible. But this could be an object also, right? But this is an object with pointers in this case. Essentially, what you have here is a node, and it points to the next node. And it has a key it can be identified with, and it could be a student ID, for example. And it has a character array that stores a name, and it has a character array that stores a school. And let's assume that we have a linked list of these nodes. Basically, you have one node, points to the other node, points to the other node, and you have a huge linked list. Let's assume that we want to traverse this linked list. And let's assume that our code looks like this. While you have a node to traverse, you check the key of the node, to check if it matches the input key. The ID of the student matches the ID that you input. And if that's the case, then you access other fields in the node and do whatever. Right? And if that's not the case, you move to the next node. Right? That's the idea. There should be an else here, perhaps, but that's okay. That's beside the point that I'm going to make. Assume you have a huge linked list, 1 billion nodes. That should be billion. It's not 1 byte nodes. We should fix that. 1 billion nodes and unique keys. Is this a good way of doing this data structure layout? So why does the code on the left have poor cache hit rate? You run this code and you figure out that, oh, this has really poor hit rate. Why do you think that is? Because these are laid out consecutively in memory. You have this node, and the node has, let's say, an 8-byte pointer, a 4-byte key, and if you see over here, it's a 32-byte name and a 32-byte school. So you have 8 bytes, 4 bytes, 32 bytes, 32 bytes. And they're all laid out in memory consecutively. If you do that, what happens is that's bigger than a cache block, right? Which means that when you do this traversal, you bring the nodes into the cache, you bring the first 64 bytes of whatever is here, and if your key doesn't match, you're not going to touch the rest of the cache line, because the rest of the cache line contains name and school, and you're not going to access those if the key doesn't match. And you go to the next node. You do the same thing for the next node. If the key doesn't match, you brought the entire cache line just to touch this next pointer and the key. And you keep doing this, and assuming you have unique keys and a huge linked list, you'd be wasting a lot of cache space, because every access, you're using only the next pointer and the key, right? And everything else is useless. So if you were smarter, you could do something else. Basically, the problem is these other fields, name and school, occupy most of the cache line, even though they're rarely accessed. And if you are a smart programmer, you realize that, oh, I'm not going to access these often. I'm going to access these less often, but I need really next and key to be able to go through the next node. What you could do is you could rewrite your program. This is one way of rewriting it, such that you have 2 objects. You have the next pointer and the key for the node, but the huge arrays of name and school, you don't put them in the same location, in the consecutive locations in memory, but you put them in a different data structure, and you have a pointer to that data structure from this data structure. And now what happens is these nodes, linked lists, if you allocate them well, they will be allocated. There will be many, many of these nodes allocated in the same cache line. Let's say this is 8 bytes, 4 bytes, 8 bytes, 8, 8, 16, 20. And if you have a 64-byte cache block, you'll have 3 of these nodes allocated. And you could access them. You could make use of the cache space. So that's the idea. Basically, the idea is, at a high level, you separate frequently used fields of a data structure and pack them into a separate data structure. And hopefully, they will be packed such that they will be in the same cache block, and you will hit more in the cache. Now, who should do this is a key question, which I'm going to leave you with. Should the programmer do this? Should the compiler do this? And how should the compiler do this? Should the hardware do this? Basically, who can determine frequently used, and who can manage it well? So if you know this at the programming level, you would definitely get better cache efficiency. Okay. I think this is a good place to stop and take a break. I hope you're okay over there. Let's take a 10-minute break and be back at 18 past. Okay, let's get started. So we're going to hopefully finish caches and cover a little bit of virtual memory. That's a concept that you should hopefully get exposed to. But before we finish caches, I want to give you a perspective of multi-core issues. We're covering not a lot of stuff in caches. Even though we've covered, I think, 1.5 lectures right now, there's a lot more in caches. In fact, the biggest conference in computer architecture is called ISCA, International Symposium on Cache Architecture. I just made a joke over there. It's really International Symposium on Computer Architecture. But there have been so many papers that have appeared about caches for 40 plus years. And they're still appearing and still appearing because it's such an important concept. And people have still not figured out what is the best way to do the caching. By the way, this is not true just for hardware architecture. There are many, many caching papers in software architecture conferences, and it's implemented in real systems also. Okay, let's talk about, let me give you a glimpse of issues that happen in multi-core systems or multi-processor systems in general. And I showed you this picture when we first started the memory hierarchy lectures, but if you look over here, there's an L2 cache, there's an L3 cache, and I said shared L3 cache. Shared means it's shared between the cores, and L2 caches in this system happen to be not shared, meaning that this L2 cache 0 is dedicated to core 0. And this L2 cache 1 is dedicated to core 1. And I'm not even showing you the L1 caches over here. It's some of these blocks over here, right? Probably the regular blocks, right? Those look like L1 caches. So caches exist, and there are different trade-offs in multi-core systems. Basically, one of the issues is cache efficiency actually becomes even more important in a multi-core or multi-threaded system, because you have more threads or more cores requiring data, and you need to cache things very well. And if you're not being intelligent about it, one core can destroy the locality of another core, or one thread can destroy the locality of another thread. And if this happens, you have not only a locality problem, not only a problem for that thread, but also a bandwidth problem, because memory bandwidth is really, really important if you're having many, many threads, as we've seen in GPUs, right? So cache space is a limited resource, memory bandwidth is a premium, so caching becomes even more important in multi-core systems. And the key question is, how do we design the cache in a multi-core system? Clearly, I'm not going to answer this question. The master's level course actually covers a lot of the design choices. There are many decisions over here. Do you make the caches shared between the cores, private to each core, or a subset of the cores share some caches? We've seen all of those designs, actually. All of these different caches exist. How do you maximize the performance of the entire system if you have many threads? How do you provide quality of service to different threads in a shared cache? This is important. You may have an application that is very intensive in terms of the cache space it requires, and you may have another application that's not very intensive, that has very good locality, but because you're sharing the cache between these two applications, the application that would otherwise have very good locality isn't getting a lot of hit rate in the caches. So that's a quality of service problem. And should cache management algorithms be aware of threads? It's probably a good idea. And actually, Intel, AMD, they are processors where you can partition the cache between different threads. How should space be allocated to threads in a shared cache? That's what I just said, actually. You could partition the cache between the different threads. But I'm not going to go into that right now. Let's take a look at one design choice, one aspect of the design choice that's relatively easy to think about. So private cache means that cache belongs to one core, as you see over here. In this case, I'm looking at the L2 cache. Shared cache means that cache is shared by multiple cores. And pictorially, it looks like this, right? These are private L2 caches. This is a shared L2 cache. And assume that they have the same space. So immediately, so this is a resource sharing idea. It is actually applied to many, many resources. You could think about other resources to be partitioned or shared. Memory controller, for example, it could be partitioned across the cores, or it could be shared between the cores. In this case, both are shared over here. But essentially, we're sharing the resource. Instead of dedicating a hardware resource to a hardware context, or thread, or a core, we're allowing multiple cores or multiple threads to use it. And all resources, you have a choice like this. Functional units, if you have a multi-threaded pipeline. The pipeline itself, you can decide to share between the threads or not share. That's the multi-threading versus single-threaded pipeline. Caches, buses, memory, ... So why do you want resource sharing? Because it improves utilization and efficiency, right? If you have one large cache, as opposed to 4 smaller caches, now you can dynamically utilize that entire cache space. Similar to what we've discussed with instruction and data. Whenever you statically partition between instructions and data, you cannot use all of the cache space for either all of data or all of instructions or any mix of instructions and data, right? Same here. If you partition the cache space between the cores, one core cannot use this other core space. As a result, you may not utilize the entire cache space really well. Again, if one core needs more than, I don't know, 64 kilobytes, too bad. It cannot get it because this other core has its own portion and it may not be using all of it. So basically, resource sharing is good because when a resource is left idle by one thread, maybe it's not used, another thread can use it. And also, there's no need to replicate shared data. If these threads are actually sharing some data, manipulating the same data, if you go back to this over here, let's say both of them, this thread requires memory address A, and this thread also requires memory address A. They both need to bring the data into their L2 caches in this case, right? Because they have private L2 caches. But in this case, you have only one copy of block A that needs to be brought, and both threads can actually access it from that shared cache. So in this case, you're wasting some cache space. In this case, you're saving that cache space when you have shared data. The same block doesn't get replicated across different private caches if you have a shared cache. Okay, so that's another aspect of improving the utilization and efficiency. This reduces communication latency. For example, data shared between multiple threads can be kept in the same cache in multi-threaded processors, just like what I discussed. You have the data, block A, that's shared by multiple threads. It stays in the same cache. If one of them writes to it, everybody sees that update because there's only one copy. Whereas if you go back to this example over here, if this core writes to block A, and if this core has already cached block A, you have a problem. Which copy is correct? This is the cache coherence problem, which I'm going to demonstrate even more pictorially, but we're not going to talk about it. So, and this is also compatible with the shared memory programming model. Shared memory programming model says that all of the threads are sharing the memory. Why not share the cache as well? But the downside is if you have resource sharing, if you have a resource that's shared between multiple different threads or contexts, this results in contention for resources. When the resource is not idle, another thread cannot use it, right? If space is occupied by one thread, another thread needs to kick that thread out and reoccupy it. And you can run into a lot of contention between different threads. This can sometimes reduce each or some thread's performance because, as I said, one application may have very good locality, another application may be streaming through memory, and the streaming application may kick out all of the blocks that this application that otherwise has good locality has. As a result, this application will not benefit from the cache, and streaming application may or may not benefit from the cache either. So you're in a lose-lose situation in that case. So thread performance can be worse than when it's run alone. Run alone means if you had the resources to yourself. This eliminates performance isolation, and you get inconsistent performance across different runs of the program. And thread performance now depends on what you're concurrently running with. So imagine a cloud computing system. You actually sent your application to Amazon's cloud, and you want some performance. In one run, you send the exact application, and exact input set, you expect the exact amount of time. But Amazon, in the cloud, in their machine, schedules both of these this application together with some other application, someone else's application, right? And they happen to share the cache, and you get some performance in the first run, 1 second, let's say, and then you send the same application just so that you can test the system. Amazon decides to schedule some other application together with your application, and this time you don't get the result for 1 hour. Why? Because the other application may be kicking out a lot of stuff from the cache, right? That's one example. That's an extreme example. But now, if you share the resources, your thread performance depends on what is the other thing that you're executing to sharing your resources with. And if you have uncontrolled sharing, you have the problem that I just described. You don't get good quality of service. Sometimes you get 1 second execution time. Sometimes you get 1 hour execution time. And this causes unfairness and starvation, which we talked about earlier. So you need to efficiently and fairly utilize a shared resource if you're sharing the resources. That's the key point over here. And we discussed this a long time ago, if you think about it, when we talked about fair memory scheduling. Okay, let's take a look at the private versus shared caches from this perspective now. So what are the advantages of shared caches? The big advantage is you get high effective capacity, right? Hopefully this is clear. We've discussed this already. You get dynamic partitioning of available cache space. There's no fragmentation due to static partitioning. If one thread doesn't utilize, one core doesn't utilize its cache space, that's okay. Some other core will take it, right? Because you have everything shared. You don't have 4 1 megabyte caches. You have a 4 megabyte cache. Okay. And it's easier to maintain coherence because a cache block is in a single location. It's not replicated across caches. We've already discussed this briefly. I'll give you the concrete problem again. The disadvantage of a shared cache is it's slower. Basically, if you have a smaller cache that's dedicated to a core, it's faster because it's smaller, and it also doesn't need to connect to many, many cores, right? Basically, a shared cache is not tightly coupled with the core. As a result, it's slower, and it cannot be customized to the core also. And we already discussed this, but cores incur conflict misses due to other cores' accesses. One core can kick out some other core's data. And some cores can destroy the hit rate of other cores. And many of the recent mechanisms that are put into the existing processors to manage the caches try to handle this problem. How do you ensure that you have a big shared cache that is very well utilized and cores get good performance out of it without one core's locality being destroyed by some other core? So people have introduced new replacement policies, new insertion policies into the caches that are aware of the cores. And Intel, for example, has introduced, actually ARM has it also, I think all processors now have it, mechanisms to be able to allocate different parts of the cache to different cores, such that this core has this part of the cache and this core has this other part of the cache, even though they're shared. Of course, you need to do it carefully because you may actually lose the resource sharing advantages if you completely partition your cache, right? Okay, so we've discussed this also. Guaranteeing a minimum level of service to each core is now harder. How much space do you give? How much bandwidth of the cache do you give? There are many, many questions over here, which, again, we're not going to cover. That's the subject of an advanced computer architecture course. Okay, let's talk about cache coherence very quickly, because I think this is some concept that you should be exposed to, but we're not going to solve the problem. I'll just give you the problem. The basic question is very simple. If multiple processors cache the same block, how do they ensure they all see a consistent state? So let's assume that the block looks like this, X. It has a value of 1,000. Let's assume that this processor loads that block into its cache. In the next time step, this processor does a loads that block into its cache. Now you have the block cached in both caches. It could happen. And this processor, what it does is it does something. It transforms the block and stores it into its cache. Now this cache is updated. Memory is not updated. What happens to this cache? Well, even more importantly, what happens when this core tries to load X from memory? Should it get 1,000? Should it get 2,000? What do you think? It's a complicated question. It should really get 2,000, assuming you're keeping these events in order. And that's what cache coherence is all about. You should not load 1,000 over here, Because this is an advanced concept, and we cover it in the computer architecture course. For the programmer to be able to reason about it, you need to keep the events in order. There is something called sequential consistency. And that's true for the same cache block as well as many, many other cache blocks as well. But basically, this processor should not load 1,000 over here. Then the key question is, how do you guarantee that it doesn't load 1,000? Well, many processors today implement what is called hardware cache coherence protocols. Basically, let's go back here. Whenever this cache writes 2,000 into this block, hardware automatically searches all of the other caches and invalidates that block from those caches. That's called the hardware cache coherence protocol. That way, there's no confusion. There's only one copy of the block that's up to date, and that's 2,000. That's one protocol, of course. The hardware could also say, oh, this processor is writing 2,000 to the block. I'm going to search all of the caches and update that block such that the value over there is 2,000 now. That's a little bit more complicated, but that's another cache coherence protocol. So you can see the complexity of this, and there are many, many design choices over here as well. So we've covered caches mainly from a single core or single thread perspective. There's a lot to do over there, but there's even a lot more to do in the multi-thread, multi-core perspective. And this is one example over here. And this problem is difficult because let's say we want to have 1 million cores on the chip, right? I know I'm exaggerating. Lots of cores. How do you actually keep the caches coherent? If you had to search all of those cores caches, then you have a problem, right? That's expensive. So there's a big debate right now in terms of how important is it to keep the coherence. Coherence, again, this is a very good example of a programmer microarchitect trade-off. The hardware could say, I don't care about the programmer, so I'm not going to support this hardware cache coherence that I just talked about. It becomes very difficult for the programmer to reason about caches in that case, right? Because caches are supposed to be invisible to the programmer. And if you actually don't support coherence in a cache system, hardware cache coherence in a cache system, then it becomes visible to the programmer necessarily. Now the programmer needs to manage the caches. It doesn't become automatically managed. So software management of coherence is very difficult. It becomes like a scratchpad memory in that case. And this was actually one of the key design choices that I believe IBM made in their cell broadband engine, which went into the PlayStations. They said, okay, coherence, we're not going to support it in our caches. We're going to have the programmer manage it. And this thing was a beast to program. As a result, they didn't continue it over time. So usually, if you get rid of support that's there for the programmer, you may actually lose. Because if you remember, there are a lot of programmers, and if your hardware is not used by those programmers, then you have a problem.